Hello and welcome to this week's lecture. We're going to cover the first, probably, I don't know, two-thirds or half of Chapter 24. We're going to look at the RCL, the resistance, capacitive and inductive AC circuits and their analysis. And we'll look at the series AC and then the parallel AC. All right, so let's take a look at this. Now, remember in DC, the voltage and currents are pretty constant, right? Once they, get their values, they stay there. Whereas in RC and RL DC circuits, as soon as the source is turned on or a switch is closed or open, it's going to have that transient response for about 5 tau. And then after 5 tau, it will be stable. And then in AC, it's constantly changing, right? The current flows first in the positive direction, then in the negative direction, and so forth. And the resistance to that change is known as the reactance, right? We have the XL, which is the inductive reactance, or XC, which is the capacitive reactance. All right. So in a circuit that has both resistance and reactance, the total opposition is known as impedance, or Z. And remember, Z equals the R plus the X. And it's a complex number. And we covered complex numbers last week. Now, and then using these complex numbers, we can analyze our circuits the same as we do with our DC. So Ohm's law, right? Voltage equals the current times the resistance is still true. So we're just going to look at it. So in the series AC circuits, the current flows the same through all the devices. And Kirchhoff's voltage law can be applied to AC circuits and states that the sum of all the voltage of the voltage source and the voltage drops equals 0. So the source equals all your drops, right? And the sum of them will be 0 because of the polarity. All right. Now, when a capacitance and a resistance are connected in series to an AC source, the sine wave voltage across the capacitor is out of phase with the sine wave voltage across the resistance. And the stored energy in the capacitor tends to oppose the applied voltage, and the voltage across the capacitor lags the voltage across the resistance by 90 degrees. So we can see this with our phasor diagram or impedance diagram. And remember, the phasor for the resistance is always at 0 degrees, right? So this one here is at 0 degrees. And then the reactance for a capacitor is at negative 90, right? So it's going down. And then, of course, X of L is a positive 90. So in this, and remember, we take R squared plus X squared, and then take the square root of that, and that gives us Z. And then we can get the angle here by taking the inverse tangent of the opposite over the adjacent, or the X is C over the R. All right. Now, in a series circuit, the current is the same. Therefore, the current is going to lead the VC by 90. And then the voltage source phasor is referenced to 0 degrees. So our voltage source starts at 0 degrees. Okay. And the current is the same throughout the circuit and is in phase with the voltage across the resistance. All right, so let's look at this now from a phasor diagram. So the red is our source voltage. The green is our voltage through our resistor. And then the blue is the current voltage through the capacitor. All right. So and then the source voltage is 10 volts, and then the current is going to be the sum of the impedance divided by 10, and that gives us our current, which is 2 milliamps. All right, so let's look at this and calculate this. Now, you're gonna, if you don't already love that Sharp calculator, you're going to when we start doing these calculations. So the traditional way to determine impedance and theta is through the use of the Pythagorean theorem and the trigonometric tangent function that we used in chapter 23, and you had in homework 11. So let's look at the Sharp. So we know that the impedance equals the resistance value, which is real, at an angle of 0 degrees, plus the capacitive reactance, which is imaginary, at negative 90 degrees. And then we know that the total current is going to be the source voltage divided by the impedance. And then the voltage through the resistance will be the current. Now remember, in a series circuit, the current is the same everywhere. So that's going to be the current, and it's going to be at the angle of the impedance. So this theta is the same as right here. So the VR is going to equal the total current at theta times the resistance value at 0 degrees. And then the capacitor voltage is going to be the total current at the angle of theta times the reactance through the capacitor at an angle of negative 90 degrees. All right. So when we look at this, we can determine, now remember, we may have to calculate the capacitance reactance by using the formula X is C equals 1 over 2 pi times the frequency times the capacitor. Now, for our purposes in this chapter, we're going to already have X of C, but you'll probably see a question on the final exam that will have you I'll give you the frequency, and then you'll have the capacitance written on the circuit, and then you have to calculate X of C. All right. And then we know Kirchhoff's voltage law says the source voltage is going to equal the sum of our voltage drops, right? Which in this case is our capacitive voltage and then our resistive voltage. All right. So if we look at this series AC circuit and it says find the impedance and theta, calculate IT, and then get VS, VC, and VR. Now, VS we already have, right? VS is 10. And then X of C is 4K, and then R is 3K. Now, one thing, and the book does this a lot, you probably, if you took a trade class or even a algebra class, you probably know that at 3, 4, if your sides are 3 and 4, 3 squared is 9, 4 squared is 16, 9 and 16 is 25. So the square root, z is always going to be 5, right? So that's the 3, 4 triangle. And then the hypotenuse will always be 5. So if you see that, you don't even have to calculate it. So we know that z is going to be 5 kilo ohms, but we do need to calculate the theta. All right, so here's the circuit that we have, and now we want to find the total impedance, the angle theta, the total current, the voltage source, the voltage across the capacitor, and the voltage across the resistor. So to do that, with the Sharp calculator, if we go into mode 3 and make sure we're in the polar mode, we can just go 3K angle 0 plus 4K angle negative 90, hit equals, and it calculates us for it. And it gives us 5K at an angle of negative 53.1 degrees. And then, so here's the steps, it shows you exactly how to do it on the calculator. And then once we have the impedance, we can take 10 volts at 0 degrees. Now remember, our source voltage is always at a reference angle of 0. So Vs at 10 at 0 divided by 5K at negative 53. And again, we're still in polar mode, and hit equals, it will say 2 milliamps at an angle of 53.1. Because remember, when we do in polar, we take 10 divided by 5K is 2 milliamps, and then 0 minus a minus 53, we get a positive 53.1. So once we know the total current, we can calculate VR just like we do in the series DC circuit, right? VR equals R times the current. So we have IT at an angle of 53.1 times R at an angle of 0, and we get 6 volts at 53.1. Then VC is going to equal the total current at theta times the reactance, capacitive reactance at negative 90, and we get 8 volts at negative 36.9. And then to do, we can calculate Vs by just summing VR plus Vc. So this is really a test on the Kirchhoff's voltage law. So we just add 6 volts at 53.1 plus 8 volts at negative 36.9, and we get 10 volts at negative 0, or at 0 degrees. Sorry. Okay, so this problem here is really, it's just Ohm's law, right? So if you think back to your Elect 50A, the DC analysis, it's the exact same thing, but now instead of just calculating the current here, first we have to solve for the total impedance, which is the combination of the imaginary and the real. Okay, so these problems are not designed to be super challenging if you understand Ohm's law, which hopefully you still do from your DC. Right now, the voltage across the resistor is in phase with the current flowing through it. In all circuits, the resistor voltage and the current are always in phase with each other. Now, the current flowing through the capacitor leads the voltage across the capacitor. Because remember, ice, right? Current comes before the voltage in a capacitor, and then it's the opposite in an inductor. So the current leads the capacitor by 90 degrees. Now, since the resistor voltage is in phase with the current, the voltage across the resistor also leads the capacitor voltage by 90 degrees. So because in the resistance part here, right, the current and the voltage are in phase, or they're together, but in a capacitive circuit, the current leads the voltage, right? ICE, current comes before voltage. So it's going to be 90 degrees between the current and the voltage. So it's going to be true of that. All right. Now, the phasor sum of the resistor and the capacitor voltage equals the source voltage, right? That's Kirchhoff's voltage law. And an angle exists between the applied voltage and the current. This angle is called the circuit phase angle, or theta. And this is an angle associated with the impedance in the series RC or RL. Now, since this is RC, theta is going to be negative because it's a positive resist or a 0 volt or 0 angle on a negative 90, so it has to be in the negative quadrant. And since XC is larger than R, theta is going to be greater than negative 45. Right? So these are just some of the rules here. So now let's do another problem where we're going to do the same thing. We're going to look for the total impedance, theta, total current, voltage across the capacitor, and voltage across the resistor. And now we have X of C is 5, the resistance is 5K, and the source voltage is 20 volts. And if we do this one, we're first going to say Z is going to be the sum of the voltage. The impedance is going to be the resistance at 0 degrees plus the reactance at 90 degrees, right? So now it's a X of C. And if we replace X of C with X of L, we'll get the same formulas that we had before. All right. So now we have an inductor. So let's there's some homework problems where you'll do this on a series. So how do we get the impedance? We would take 5K angle 0 plus X of C, which is 5K at an angle negative 90, it equals, and that will give us our Z and our theta for the impedance. Then we could take, we know IT is going to be Vs, which will be 20 volts at 0 degrees, divided by Z at whatever that angle is, and that will give us our theta for the current. Then VC is going to be R, which will be 5K at 0 degrees, times IT, and then X of C will be 5K at negative 90 degrees times IT. So that you can calculate those very simple. Now, in an inductor, it's just positive 90 degrees. All the formulas are exactly the same. And Kirchhoff's law is still true. The voltage across the resistor plus the voltage across the inductor equals the source voltage. Now, another thing you can do on these problems, if you're given, let's go back here. If you're given Vs and you calculate VR, you can just take Vs minus VR and it equals Vc, right? It's the same. I mean, the same principles. And then Kirchhoff's voltage law, it has to be true too. All right, so here's where we do it with this circuit. So now we have a source voltage of 100 volts. We have a resistance of 8K. We have an inductor with the inductive reactance at 6K. And we're going to calculate impedance, theta, total current, voltage across the inductor, voltage across the resistor. And then we'll do a Vs equals VL plus VR to prove that KVL is true. All right, so here you go, right? Using your sharp calculator, 8K angle 0 plus 6K angle 90 equals 10K at an angle 36.9. IT is going to be 100 volts at 0 divided by 10K at negative 36.9 is going to be 10 milliamps at negative 36.9. And then VR is going to be IT times R. VL is going to be IT times X of L. And then Vs is going to be equal to the sum of VR plus VL. All right. So very, very straightforward. And the only thing different between this and DC is that our angle, that we're dealing with complex numbers. So we have to go in a complex mode and then make sure we're in the polar mode, and then we can do all of this math. And the sharp calculator, if you don't love the sharp calculator after today, I don't know what to tell you. I mean, you don't have any love in your heart for anything. So, of course, I'm joking. All right, so now we know the voltage across the resistor is in phase with the current flowing through it. In all circuits, resistor voltage and current are always in phase. The current flowing through the inductor lags the voltage across the inductor by 90 degrees. Remember, the voltage leads the inductor, or the inductance. So, no, the voltage it leads the current. I is for current, not inductor in there. Okay, and then away you go. Now with an RL circuit, it's going to be positive. It's always, the theta is always positive, and if R is larger than X of L, theta is less than 45 degrees. Or if X of L is greater than R, it's going to be greater than 45 degrees. All right, so here's another problem that you can do. Find Z, theta, IT, VL, and VR. And you'll do this in the homework coming up. All right, so this is when an inductance and a capacitor are connected in series. So now we have both R, V, or X of L and X of C. We just have to add up all the values. So now the traditional solution to the total impedance of the RLC series circuit is in rectangular form, is the resistance plus the J X of L minus X of C. And in polar, you just go R at 0 plus X of L at 90 plus X of C at negative 90. And theta is positive or negative depending on which value X of L or X of C is a larger quantity. So if X of L is greater, theta will be negative. If X of L is larger, theta is going to be positive. If X of C is greater, it's going to be negative. All right? So all other circuit values are the same. So now the source voltage, Kirchhoff's voltage law, is VR plus VC plus VL has to equal VS. Or if you say 10 minus all this, it should equal 0. All right, so now we have a circuit here where we're going to find theta. We're going to find Z, total current, voltage across the resistor, voltage across the capacitor, and voltage across the inductor, and then prove Kirchhoff's voltage law is true. So this just shows all of it. So again, you start with Z by saying your 3.3 kilo ohm resistor at 0 degrees plus a 7.5 K inductive reactance across the inductor at 90 degrees plus the 5.3 K at negative 90, which is the X of C, and that comes out to 3.9 K at 33.7. Then the total current, again, is just the source voltage divided by the total impedance, which will be 4 volts at 0 divided by 3.97 K at 33.7, and you get 3.52 milliamps at negative 33.7. Then if you just do the calculations, VR is going to be the total current times the resistance. DC is going to be the total current times the capacitive inductance. VL is going to be the total current times the inductive reactance. Yeah, I said capacitive inductance. That's capacitive reactance. And then prove it by saying 10 or 14 volts is going to be the sum of all these added up, which it will be. All right. So then if we show this in the phasor diagram, we can see that the VL plus VR plus VR plus VS plus, it's all going to sum up, and then here's our VC. If you add all that up, it will equal 14 volts, right? And then there's our angle theta. Now, because our capacitive reactance was greater, that's why we get a negative value here. All right? And then here's some definitions for that. And here's another problem you can do. And we'll do some of these example problems in next week's video. I'll do some practice problems. But for now, you should have more than enough to do this week's homework. All right, now parallel. Parallel is the same concept, except for we know that instead of the current being the same everywhere, the voltage across each branch is the same. So now all we have to do now is um, uh, find the current, just like the voltage is the focus of a series circuit. So the voltage is the same across the resistance and the capacitor. The voltage source has a reference phase angle of 0. So the current through the resistance, IR, is in phase with Vs and therefore also has a phase angle of 0. The current through the capacitor, IC, leads VC, right, Iceman, and then the current through the inductor lags the voltage. So here we have the source voltage, we have VR, we have VC, and we'll have our angle here. All right. So now IR and IC are found by Ohm's law. So we know that VR is going to equal Vs, because whatever this is going to be between these 2 points, and whatever it is there, it's going to be on this node, right? In parallel, the voltage through each branch, or the voltage across each branch is the same. And in this case, it's going to be the same as the source voltage. So we can get IR here and then IC here with this. So IR equals the source voltage divided by the resistance. And then IC is going to be the source voltage divided by the capacitive reactance. Then the total current in the parallel circuit is the sum of the branch currents. So remember, we have a current that will flow this direction and another current that will flow this direction. And when they come back here, and here's our total current right here, when it comes back in, the sum of this current and the sum of this current has to equal it. So that's where we'll do IT equals IR plus IC, and away we go. And then once we get the total current and we know this total voltage, we can divide those to get our equivalent impedance, right? So let's find IR, IC, IT, theta, and the equivalent impedance and draw the phasor diagrams. So now we have 12 volts. So VR is going to be 12 volts, or IR is going to be 12 volts divided by 750K. And then IC is going to be 12 volts divided by 800 ohms at negative 90. This will be at 0. And that will give us IR and IC. IT will be the sum of those. And then Z equivalent will be, and once we get IT, that's where we get theta. And then once we have theta, we can do um, the Vs divided by IT will equal the total, the impedance. So Vs divided by IT, and away we go. And then to draw the phasor diagram, we know IR is a value, right? It's 16 milliamps, and we're going to do the current here. And remember, this is a capacitor, so the current uh, leads the resistance, right? ICE, or leads the voltage, ICE. And then we get IT with theta, and away we go. And because this is the current is leading, it's going to be positive. All right. So here's another one that you can do where, and this is in the book, so you can find the answers in the book and then do it. All right. Now in parallel AC circuits, the voltage is the same across the resistance and the inductance. The voltage across the source has a reference angle of 0, and then the current through the inductance, IL, lags the source voltage by 90 degrees. So now it's the same thing, just now instead of a negative 90, we're doing a positive 90. And then the current is going to be, instead of a positive 90 like it was in IC, it's going to be a negative 90. So theta is going to have a negative sign for parallel. It's going to be a positive sign for RC. All right, so here we go again. So what is the current through IR, it's going to be Vs divided by 5K, which would be 2 milliamps at 0 degrees. And then what's the current through this inductor will be 10 volts divided by 4K will be 2.5 at a negative value, right? So that's going to be negative 90, 0 degrees. And then IT is going to be a total of IR plus IL. And then that's where we get theta here. And then VS is going to be, or is the equivalent impedance, or the total impedance will be the source voltage divided by the current. And that's it. So that gets us through series parallel RLC AC circuit analysis. All right, so now here's a combination circuit where it's both IR, IL, and IC. So now we're going to have IR, IL, and IC. And we can calculate this with the total is just IR plus IC plus IL. And it's going to be positive or negative depending on which one's the larger quantity. And then our equivalent resistance or impedance is going to be 1 over the resistance plus 1 over the capacitive reactance and plus 1 over the inductive reactance. Okay, so you can look at this example and see how to do that. All right. So then as a check, we can say that the reciprocal equation to find it. Now, these other ones, we're just doing IT, and then we can say ZQ is still going to be VS divided by IT. We can also check it by taking the parallel resistance formula, right, which is Z equals 1 over the resistance plus the capacitor reactance plus the inductive reactance. All right. And then here's finally one more example problem. And now we're going to remember in DC, the concept of conductance, or G, is useful to help analyze circuit, and it's the reciprocal of the resistance. So it's 1 over R. And conductance is additive in parallel DC circuits. So in parallel AC circuits, the concepts of susceptance and admittance are used to analyze an AC circuit. We're not going to do a lot with that, but I'm just going to introduce it here. So the B is the susceptance and Y is the admittance. So B is going to be 1 over the reactance, and Y is going to be 1 over the impedance. All right? And then you can find that there. All right, so hopefully that gives you a good understanding of the first, I think that's the first 64 slides in chapter 24, and then we'll do the last 30-some slides next week in the next video. All right, well, take care, and of course, let me know if you have any questions, and I'll see you later.